Hello everyone, my name's Dane. In this video, we're going to be going through my roadmap for reliability engineering and asset analytics for 2024. And we're going to be covering the types of skills that I think that you should be learning if you were to get into this field in the next year. Now, this type of content is my opinion. If you think I've missed something or you disagree with what I'm saying, please leave it in the comments below. If you like this type of content, hit the like button and subscribe to the channel to get more videos like this. I've included a link to this mind map in the description below. And just to understand what you're looking at here, everything that I think are core skills and things you must know are in the green boxes, and the good to know supplementary type stuff is in the orange boxes. Starting off at the top, the first thing I think you should know is the general asset management standards for this discipline. So ISO 55000, 55001, 55002, and they really set the stage on what we're trying to achieve in terms of maximization of value, continuous improvement. A lot of the kind of core values of this discipline are illustrated throughout those standards. The next thing is to have a good fundamental understanding of financial metrics and things like financial valuation. So we're talking NPV and all the net present value and all those type of metrics that go along with it, like rate of return, return on investment, cost benefit ratios, that kind of thing. It's also good to have some knowledge around other types of financial metrics, what depreciation is, what weighted average cost of capital is, what inflation is, and how to account for those in your calculations. Because a lot of the things that we need to be doing in this discipline is justification of investments and justification of changing things like maintenance strategy and changing the way we do business. And a lot of the time that boils down to financial metrics. Next up is having a really good understanding of causation and what causation is. So cause and effect. It ties into a bunch of different tools and sort of sub-disciplines within asset management. And so root cause analysis is a prime example. Performing root cause analysis on determining what led to a specific event that you want to prevent in the future. That is typically a chain of cause, effect, cause, effect, cause, effect, leading to the outcome. Similar with 5 whys, it's the same sort of thing. Why did this happen? Why did this happen? Why did this happen? All cause and effect. We look at causes in terms of causes of failure modes in RCM context. So it's really key to have a really good understanding of how cause and effect works in the physical world. So getting your head around RCA, 5 whys, and causal models is a really good start. Next up, I highly recommend you become familiar with the methods that we use, spanning back, since the 60s. A lot of these things are quite old and now becoming redundant, but they have great fundamentals in there that you should understand and know, so you know what's important to do and why, and what you can move away from with some of the newer methodologies and approaches that are coming out. So the historical ones are failure modes and effects analysis, or FMEA, failure modes, effects, and criticality analysis, or FMECA, and reliability centered maintenance, RCM. It's important to understand the history, where they come from, how they were born, because then it gives you an insight into understanding like what their use cases are, what they're good at, what they're not so good at. And you really need to understand the methodology behind each one. So what are the steps that you're going to be doing when you perform a FMEA, FMECA, or RCM type process? And which of it is around asset knowledge capture, and what stuff in there is like business decision making, business process. Another one that I recommend you look into is the CNAIM. It's the Common Network Asset Indices methodology out of the UK. It does have a bunch of issues with it in terms of mathematical correctness and the way it approaches certain things, but it's got some really cool ideas baked into that approach, and just understanding like what can be done in terms of scalability of this type of analytics. The CNAIM is a really cool initiative that's ongoing in the UK. All right, up next is statistics. So having a really good understanding of statistics and probability distributions and that kind of thing is key to this discipline as well. So let's start with becoming familiar around various different distributions. Weibull distribution or Weibull distribution is the main one that we use in this discipline. You will be exposed to other ones like normal and Poisson and binomial distributions and so on. But when we come back to understanding physical assets, the one that's the most flexible and the one that fits the most of the sort of tasks that we need to do is the Weibull distribution. So read up on that one, understand, the 1, 2, 3 parameter Weibull, And then also fitting data. So how do we take failure data out in the field and other types of data and fit it to a distribution? So this is, the methodologies that we use to fit it, whether it's, regression or least mean squared or all those type of techniques to fit a data set to a distribution, understand how that works, understand how you can do it, and become familiar with some of the tool sets that are out there that you can plug your data in and get the distributions out that you want. Next up is common data traps. And unfortunately, experience is really the only good teacher in this space. What I'm talking about here is left-censored, right-censored data, dealing with outliers, and how to unpack the problem when your data set doesn't match what you would expect in reality and what general engineering principles would suggest happens, and the data doesn't match that. How do you deal with it? So lastly, in the statistics area, there's general distribution manipulation. This is moving between things like hazard functions, probability density functions, and cumulative density functions, understanding the formulas and how to go from one to the other. Then we move into the space of risks and benefits. Foundational understanding of probability and consequence, and probability of consequence as well. Getting your head around risk matrices. They're a common tool used in many businesses today. There are better ways to quantify risk, but because it's so widely adopted, you really need to understand the fundamentals of risk matrices. Various consequence categories that are relevant to your industry. So things like environmental risk, safety risk, stakeholder risk, reputational risk, all of that kind of stuff. Criticality, it's not so important to know. People are moving away from criticality because of the ambiguity around it, but understanding things like risk priority number and how criticality is handled in things like FAMICA approaches and that kind of thing is still really good to understand, but I'd be suggesting that you steer away from criticality and use more consequence and risk type approaches. Industry specific benefits and measures. So each industry has their own set of measures and specific KPIs and targets and things that they want to use. So things like power industries have, SAIDI, SAFE, STIPUS, all of that kind of thing. And understanding those at a fundamental level, what they are, what they measure, how you're going to calculate them, is really good to know. Value frameworks, another core competency, let's say, in this area. So value frameworks is around quantification of risk, monetization of consequences, and putting everything that we value or the business values on a level playing field so we can make better decisions around that. Lastly, in this space, we have service measures. It's somewhat of a double up of the industry specific benefits and measures, but the focus of this one is more around solving different types of like mixed integer programming problems and things like that, which we'll cover in a second, and understanding how we can constrain on various different targets and budgets and resource profiles and things like that. Next up is condition assessment, understanding how we can condition assess an asset. This is drawing the links between what an inspection or condition assessment task or condition monitoring type technology can look for and can detect, and what that tells us about the asset and how we can infer future likelihoods of failure and future degradation of the asset from that condition assessment point. It's also important to know health scores, indices, methodologies for calculation of health scores and indices. Although somewhat similar to criticality, health scores and indices are slowly going away, and people are adopting more of a probability of failure and hence risk look of their assets to determine when they should intervene. So condition monitoring, understanding the different types of ConMon techniques, from thermography to vibration analysis to current draw, signature analysis, there's a whole load of them. They're basically tools that you can use to get more information. So having a really good grasp of all the different tools that are out there to get more information about your assets out in the field is fundamental. But how they actually work internally, like the details, if you're looking at like vibration analysis, something, and like understanding like fast Fourier transforms and that kind of stuff, really, really cool to know. Not necessary but how they work from an engineering point of view. Then we move into the solver space. Once we understand our assets, we need to use that information to make good business decisions. And the tooling that's out there typically has some sort of engine that sits behind it or calculation process that sits behind it. And there's various different types that are good for solving different types of problems. Monte Carlo simulation is one. Having a good grasp of what it is, what it's good at calculating, what its drawbacks are, is a must know. Other tooling use things like distribution aggregation and projection, which sits firmly in the statistics space. Some use decision trees and bow ties, and others use things like mixed integer programming, mixed integer linear programming to solve different types of problems. These ones are really cool because a lot of the problems that are coming out in industry at the moment is how do we make better decisions with our data? Where do we invest our money, into which assets and to which options and things like that. And so mixed integer programming is a really good way of solving these types of problems. Understanding constraints, budgetary constraints, resource constraints, targets constraints, and how you formulate the problem and formulate the objective function of these type of programs is really cool to know as well. There are some open libraries out there like Pulp and Coin. I'd suggest that you start using those for these types of problems to begin with, and then you can start looking into the more commercial libraries like Gurobi if you hit the ceiling or the limitations of the free ones. The commercial ones are typically a lot faster. They solve problems quicker, but you can still get really, really good results out of the free Pulp and Coin libraries. Next up is tasks. What I'm talking about here is detection tasks and corrective tasks. I'm going to use this terminology, but basically what I mean here is detection tasks are things like your fault finding tasks, your condition monitoring tasks, which do not impact the asset in any way. Under this, there's certain concepts that you'll need to understand, like detection probability and PF interval, or potential failure to failure interval, and the time it takes between when you inspect something to when it will degrade to a failed state. These play a really big part in things like maintenance strategy optimization and determining intervals of when you should do various different tasks. And then on the corrective task side, those tasks that actually impact the asset, what they impact, what failure modes they reset, and how much they adjust where the condition was before to, or not condition, where the probability of failure was for certain different modes before to where it is after once the corrective tasks performed. Then we have asset versus system view. So we can look at asset management problems and reliability engineering problems at different sort of levels, starting off at like component level to asset level to system level to more holistic kind of portfolio and business level problems. Some of the ones that are in the asset space versus system space, reliability block diagrams is really cool at analyzing systems where they're all interconnected and there's dependency between various streams of one system and other streams. So understanding reliability block diagrams, and then life cycle cost. How do we calculate life cycle cost? Incorporation of both CapEx and OpEx type tasks into the cost profiles. Once you have a really good grasp of that, I think that is a great start for getting into the reliability engineering and asset analytics space for 2024. Most importantly, keep learning. Thanks for listening, and I'll catch you in the next one.